this computer. All right, so I guess it's recording now. So everybody was okay, right, with recording? No complaint. And I'm gonna share my screen now. This is my first time, so they might have glitches or anything. So here it is. All right. So guys, see the video? Yeah, the Word document. Yes.
Yeah.
All right. Cool. So this is problem number 1 actually in your book. This is one part of it. In that problem, it asks you to do multiple calculations, but we will just do one piece of set of engine calculations. If you look at problem, I don't know if you guys have access to the book in front of you or not. But what it asks you is there are some data on a diesel engine operating in a brake, and in the book there are like 4 engine speeds, 4 torques, 4 fuel consumptions given to you, and then there are 3 parts in that problem that you need to do the calculations for. This is just one part of that, one engine speed that I just copied and pasted here. It's at 1000 RPM. 1550 feet-pound force, and fuel consumption 19.7 gallons per hour. So if you go back to slides, remember the power system. Oh, you guys can't see that, right? Let me stop sharing and reshare because I have to share my whole screen with you guys. Okay. You guys see the screen here? So this was the engine, right? So it's a simplified drilling engine basically, and there is a power input to this system. The shaft rotates, right? Once the shaft rotates, then if you have a weight here, it can raise it or lower it down, right? What do we raise or lower down? Anybody? What is in drilling? What when we do the drilling, what are we raising or lowering?
Drill pipe or wire line.
Yeah, drill pipe, which we call it basically a stance, right? The stance are 3 bells of those drill pipes. For example, 3 drill pipe attached together is a 3 bell, or they call it drill stand. Okay, the length is usually 90 feet, but that's not the only part. So there are many of those stands depending on the depth of the wellbore that we are drilling, right? So we need to raise it, we need to lower it as we drill deeper into the formations, right? So drill bit, some other things also attached there, but the main weight is basically from that drill stand. So we want to raise it, lower it, and this is done by this rotation, right? So power in general is defined as force multiplied by velocity, okay? Anybody can tell me the difference between power and force? Yeah, conceptually, what is the difference between power and force?
Power includes the velocity and the force.
Force is just a force, right? So you move an object from this location to another location for a distance d, right? Now, I may do it in 10 seconds, right? Cayman may do it in 2 seconds, right? We both applied the same force and we moved that object for the same distance, right? But I did it slower than Cayman. So there we say that Cayman have more power than me, okay? And power basically includes the time that force being applied and do basically the same work, right? And work is defined as force multiplied by distance, right? So that's basically the difference between power and force. And the power for this engine is omega multiplied by r, right? Omega is the angular velocity of this shaft. This is shaft, right? R is this radius here, right? So this rotates, produce a power omega multiplied by, I said multiplied by R, omega multiplied by torque, right? And torque is force, this force that is kind of trying to rotate this shaft multiplied by this radius, right? The radius of the shaft. So also the omega is 2 pi Rn, sorry, 2 pi N, and is revolution per minute, right? How fast this shaft is rotating, right? Anyway, so that's the input power, right? And then that's one thing that we want to calculate first here, right? So we have the speed engine, right? 1000 RPM. So what is that? Which of those symbols that we just talked about is 1000 here?
Should be N.
Sorry?
N. Should be N.
It should be N, right? Exactly. So N is 1000 RPM. And what else? We have the torque, right? So T is 1550 feet pound force. Fuel consumption. So what is fuel consumption? Let me go back here to the slides. So fuel consumption relates to whatever is coming to the engine, right? So fuel provides the power for the engine, right? Here we have a diesel engine, and diesel engine is basically this table. This is the table you want to refer to. It has a density of 7.2 pound per gallon, right? Is it higher than water or lower than water? 7.2.
Lower.
Lower, right? What was the water density yesterday you guys measured?
8.3.
8.33, right? So 8.33 ppg was the water density. So this is lower than water. So oil usually have a lower density than water, right? So this is 7.2 compared to that one. And it's 19,000 BTU, British thermal unit per pound mass. So it means that if you burn 1 pound mass of diesel, it will produce 19,000 BTU energy, okay? So we had also this, right? The heat energy input to the engine, and this is that equation. So Q is the input, right? Feet pound force per minute. W is the rate of fuel consumption, and H is the heating value, right? So heating value listed here, 19,000. So I can go back there. Heating value, because this is a 19, sorry for my writing. 19,000, what was the unit? BTU per pound mass. And what else we have here? We have that number as well, which is the density, right? Pound per gallon, 7.2. So density, 7.2 pounds per gallon. By the way, you can use all the, you will bring your cheat sheet or equation sheet to the exam. So you will have all this equation written for yourself, but just try to understand what do they do, okay? So now what we want to calculate at the first one is the horsepower, right? So P, horsepower, is equal to omega T, right? That's the engine horsepower, right? And omega, which is the angular velocity, is equal to 2 pi n, right? So for your homework, you can create a table in the Excel sheet and just do all the calculations in the Excel sheet, right? But just make sure when you want to submit your homework, write what equations you have used there in that Excel sheet, okay? So now the engine speed was that, right? The torque, we have that one. So omega is equal to 2 pi multiplied by n, which is in this case 1000, right? So pi here is 3.14 multiplied by 2 multiplied by 1000, right? So you will get 6,283.2 radian per minute. Be careful about the units, okay? What units you're putting. So this is RPM, revolution per minute, right? And why, anybody knows why we have a 2 pi there? Any idea?
Is it because the drive shaft is circular? Or, I mean, not the drive shaft, but the pulley is circular?
Yeah, that shaft is circular, right? So if it rotates one full circulation, one full rotation, right? So if you have this, it rotates one complete rotation, right? That is equal to 2 pi, right?
Yeah.
So basically what we are doing here is converting one revolution to radian. So one revolution is 2 pi radian, right? That's why the unit changed to radian per minute. Okay, so this is basically a conversion factor. N itself is also angular velocity, but the unit is different. So what all we do here is change the unit to radian per minute. Okay, so that's omega, right? And then we can calculate P because we do have the value of torque as well, right? So that is omega, which is 6,283.2. Unit is radian per minute, multiplied by the torque, which is whatever that is, 1,550 feet pound force. Make sense? All right, so now, is that the unit we use for calculations? What unit should we present power in? Horsepower, right? What is the conversion factor?
33,000.
Exactly, 33,000. We divide it, right? Feet, pound force per horsepower, right? So once we did that calculation, we do this conversion factor. And if we do that calculation, we get 295.12 horsepower, right? So the book, have the answer, right, as well, in front of it, right? So you can make sure that you have the right answer. So for second one, which is what we are doing here, right? It's 295.1, right? Sometimes the book answers are not correct though. We'll get there later on, but it's correct here. So any questions in this part A? Nope.
What happens to the rad per minute? Is it just absorbed into the horsepower?
Yeah, so yeah, exactly. So that unit conversion, so what we get after on the numerator of this thing, right, is radian is actually doesn't have radian or revolution. They are there still, okay?
Yeah.
But we don't count them usually. We don't write
Okay.
them, right? Sometimes you may see the speed to be written in terms of 1/time, right? They even don't mention what is that. It's a rotation usually that they don't write it, okay?
Okay.
So it's absorbed, yeah, it's there, but we don't just write it. Any other questions? So is this the input or is this the output horsepower? That
Would
we
this
just
be the output horsepower because you're already including the radians?
Exactly, yeah. This is the output horsepower of the engine, right? How the input horsepower is calculated? I have to, let's see. Create a new page here, okay. All right, so this was the output. The input is using the diesel, right? Diesel is providing us the input, right? So next part, which is part B, it is asking us to calculate the overall engine efficiency at each engine speed, right? Now here the engine speed is 1000. We want to calculate it for that specific engine speed, right? So overall efficiency equation. Efficiency in general is the output power to the input power, right? For anything, for any type of system, it doesn't matter. So the output, we show it with P, the input, we show it with Q, right? And Q was the input from the diesel engine, right? And based on the presentation, Q was calculated using this equation, right? So it's WF multiplied by H. So I'm gonna go there. QI is WF multiplied by H, right? We do have the heating value, right? Calculated, or just from the table, right? 19,000, right? So this value is 19,000. And this WF, what is the unit of this? Pound per minute, right? Pound mass per minute. Do we have this number from the information we have here? From the fuel, what we have is this fuel consumption, right? Which is gallon per hour, and we have the density, right? These two information we have from the fuel. So, but we need to convert this into what? Into pound mass per minute, right? How should we do that?
Fuel consumption times the density.
Exactly. So if you multiply this number by that number, the gallons will cancel out, right? And what you get is pound per hour, right? So it's basically converting volume into mass. And in order to do that, you need the density, right? So, and that is the density here, right? So 19.7, so WF is 19.7 unit gallon per hour multiplied by 7.2 pound mass per gallon, right? Pound per gallon. So if you multiply these two to each other, you get, let me see, what would that be? So 19.7 multiplied by 7.2, that's 141.84. And that's pound mass per hour, right? Now that's WF, we have H as well, right? So QI is 141.84 multiplied by 19,000, right? And that is equal to, so this is BTU, right? This is pound mass per hour, right? And what would be this? Oh, we need to convert hour to minute as well, right? Because that's how we report the conversion that we have is when we have a minute, right? Feet, pound, force, eventually that we report there, right? So 1 hour is 60 minutes, right? So this calculation, if we do that, you multiply that, and eventually, what conversion factor again you need to use? That's 30,000 again, right? 33,000 feet pound force per minute per horsepower. Did I forget to put minute here? Yes, I did. This is per minute here, right? The conversion that we have there. I forgot to put the minute. So feet pound force per minute to horsepower, that's there, right? Here also feet pound force per minute to horsepower is 33,000. Make sense? So QI is going to be in horsepower units. We should get 1059.16 horsepower, right? And this is, I'm going to, what am I doing? I'm trying to create a new page, hopefully. All right, a new page is created. Another page is also created. Okay, so efficiency, right, is P over QI. P was calculated to 95.12. QI is 1059.16, both in horsepower, so you should get 27% efficiency based on this, right? So that's part B. Any questions in part B? Nope. All right, so finally part C is compute the fuel consumption in gallons per day for an average engine speed of 8. This is not 800, we're doing it for 1000, right? The book is asking you to do it for 800, but let's do it for 1000 here. We're doing the calculation for. So fuel consumption in gallons per day, right? How should we do that calculation? So we are using 19.7 gallons per hour, right? That's what the problem is telling us, 19.7 gallons per hour. And we want to calculate that in a 12-hour workday, right? You just multiply it by 12 hours. That's it. So that's how much you use in order in one day, right? And that is equal to 12 multiplied by 19.7. That's 236.4, right? Gallons per day. Done. Right?
Why do you do 12 hours for a day?
It's mentioned in the problem.
Oh, okay. Okay.
Yeah, yeah. It's mentioned, and also 19.7 is there too, right? So we just need to multiply them together.
Yeah, I just didn't see the
Okay.
12 hour per day.
Yeah. All right. So the reason that I have this because this is 12 hours per day, right? Work day, I should say. Work day. Right, 12 hours per work day. So that's 236 gallons per work day, right? Okay, any questions? No. What did I do? Okay. Any questions? Any part that is confusing? Nope. So I'm gonna stop sharing here. So that was the problem we wanted to do, and let me stop the recording as well.